That was funny. Your response was classic.
Our next speaker is Bryan Singer. Bryan is a principal consultant with Nexus Security Corporation. He's got more than 18 years experience in IT security, including 12 years specializing in industrial automation and control system security. He's got a lot of experience with OSINT, counterterrorism, forensics, pen testing, vulnerability research, cybersecurity assessments for over 3,000 industrial processes worldwide. He is the founding past chairman of ISO 99, 62443, current director-elect of the ICS Safety and Security Division, and co-author of Cybersecurity for Industrial Control Systems. He is a frequent speaker and trainer for all things industrial control systems in regards to security. Bryan's topic is building on device vulnerabilities, attack modes, or ICS. Please give your attention to Bryan.
Good morning, everybody. So I realize I'm between you and lunch. I'll tell you, I'll try to make it quick, but that's a fair warning. I'm probably the world's fastest talking Southerner. So I don't know if you want me to do that or not. We'll see how it goes. So anyway, actually, thank you for the introduction. I appreciate it. Folks, curiosity here, is there anybody here that's actually a plant operator, anybody that's in an industrial setting? That's what I was afraid of. Anybody here that's working in industrial control security research or any type, other than I know Dr. Long and a few others out here? Okay, not a whole lot. Didn't really expect that today. I'm going to be taking this. I am actually an IT security person by trade, software developer by trade, but I've been working in industrial automation for a number of years now, since about 1997. So again, basically, my normal wear every day is Nomex and hard hat and safety glasses and steel toes, and I did some tie today because I didn't feel like passing out in front of you, but this is not my normal wear. So obviously, I've made my bones mostly working inside in the industrial automation space, and so I really did take the tack in this presentation that we'll focus a little bit more on the engineering aspect because, again, everybody's talking about industrial control security these days, but one of the issues you run into is that people are chasing the wrong problems in many cases. So, really quickly, why do I need ICS, industrial control? Oh, by the way, if anybody has any questions, I know I heard a couple this morning from Dr. Vaughn about control systems themselves, how do they work, what are their vulnerabilities. Again, I actually worked for Rockwell Automation for a number of years. I worked with almost all the major vendors, either doing testing or vulnerability research or pen testing or all kinds of other things for them. So I'd be glad to talk to you what I can about any of those. What do industrial control systems actually do? How do they work? I'd be glad to answer any questions around the lines. So what do we need ICS security? One thing that people don't understand, I'll just kind of jump to the bottom point here first, is that in the IT environment, we use information to drive decisions. Right? We make decisions based upon things that are going on the IT side. But within the industrial control setting, the major difference that we see for industrial devices is that we use information to drive physics. We actually make, we make valves open and close. We make sensors move. We alert on sensors. We turn drives, turn motors, we turn controllers. We open up burners. We change temperatures. We add oxygen to it. I mean, we can cause things to go very bad very quickly. Right? So we actually are dealing with the fact. And yes, I realize that that's a little bit of an oversimplification because in IT we also have like HVAC systems and fire control systems and some other things like that. But again, on the whole, usually within an IT space, about the worst thing that's going to happen is I'm going to lose my email, I'm going to lose my B2B systems and things like that. Within an industrial control setting, a lot of those impacts are just the beginning. Right? We look at the fact that we can now actually cause very physical damage, we can cause very protracted outages, we can cause what we call the crater factor. We leave a big smoking hole in the ground as opposed to losing email for a few hours. Okay, so I don't know if anybody here has actually ever done any vulnerability research, but this is a conversation that I have actually probably had very close to this, I'm kind of ashamed to say. But it's a very typical conversation that we see a lot of times with plant operators these days. So a security researcher goes through and they do an assessment and they come back and they say, oh, we have 438 critical vulnerabilities. So in other words, they run Nessus or they run Expose or they've done something like that, come back with a list of 438 critical vulnerabilities you have to do something about right away. And they go talk to the plant manager. You've got to do this, you've got to take care of these vulnerabilities right away. I can take control of your PLC or your controller from across the internet and do X nasty thing. Plant manager goes, so what? I'm not connected to the internet. So the security research is undeterred, says, I can write a worm that'll put the PLC in an overspeed and that will make the PLC overspeed the turbine generator and put it into a surge condition. Surge is not good. High vibration, things start falling apart. Okay? Plant manager goes, good luck, there's a machine protective system to separate from the PLC. In other words, there's another electronic component to test the speed of that component to make sure that it's not going into surge and shut it down. So in other words, there's more than one device out there. Well, fine, you need to patch all these vulnerabilities anyway. Plant manager goes, okay, my next scheduled shutdown is 333 days, and it costs me $8 million an hour to be shut down. So this is important enough for all these vulnerabilities to warrant me shutting down the plant to put all these patches in place. Security researcher, folks like us in the room, we see 438 critical vulnerabilities and think you absolutely ought to do something about that, right? So we tell them, of course you should. Plant manager goes, I don't process credit cards, I don't run public websites, I don't have HIPAA health insurance information on here, why do I care about this? So the security researcher next says, oh, well fine, I'll tell you what, I'll take control of your boiler and I'll blow it up. So you set the PLC in the boiler to overpressure the boiler? Absolutely. The plant manager looks at him and goes undeterred, there's a relief valve on that. Have a nice day, I'm done talking to you. Okay? This is a very typical conversation for industrial control security folks these days because, again, we're trying to tackle the wrong problem. We're not attracting in the right direction. So what I've seen like somebody come out recently, I saw a bunch of vulnerability reports for, I won't mention it, but it was like a Rockwell or Siemens or something like that. It said, oh, well, there's a remote control exploit vulnerability that I can launch the string because these string of commands and I can shut down the PLC remotely. Like, so what? The Modbus stop. The protocol command is therefore does exactly the same thing. Why do I need a vulnerability to do exactly that? Right? The idea of attacking an individual device in an industrial control system space means absolutely nothing to most of us. All right. So for a plant manager, if you're going to talk to these folks, you're doing these types of assessments, you've got to be able to handle this. Oversimplification again, but first of all, what is the vulnerability? Second, is it real? Third, what do you do about it? If you don't know how to answer all three of those questions, you're basic. I already went to Orlando. But see, honestly, that should tell you something about what I know. It says, bring your suit. Okay. What is it? Is it real? What do I do about it? And there's the issue we also think about, too. Again, a lot of times, us as researchers will go in and we'll talk to folks. And this could apply anywhere, even if you're not in an industrial setting. You've got to know your audience. You've got to know the business you're working with, correct? So we walk in and we start talking to these folks and tell them what the risks are. You better be able to show them that it's actually something they need to be concerned about. Now, for like a plant manager in my space, if you make them aware of a potential safety threat, something that's a danger to health and human welfare, they are legally bound to do something about it, right? So if you walk in the door and you alert them to the possibility of a risk, something that could be a danger to health and human welfare, if you don't have something to back that up, you're liable to get sued. You're definitely going to get escorted off the site, and yes, I actually speak from experience from many years ago when I first started doing this. That was the end of the day when I was told, yep, we showed them that there was something very real, but we didn't have something that would actually solve it, and that was the end of the conversation. Right? Okay. So there's a few things about industrial control. We talked about industrial control. Again, we did the traditional models of confidentiality, integrity, and availability that most of us are all familiar with. Yes, I know we all like to rearrange these acronyms. It really kind of doesn't matter. The whole point here is that we need quite a bit more to understand the industrial control system side. Well, I say basically that this is an engineering problem that requires engineering solutions. Now, myself as an IT person, myself as an IT security person, as a software developer, I have a hard time admitting it's not something that I can solve. As far as I'm concerned, the whole world's a nail, right? So, excuse me. However, the thing that we need to understand, in order to protect an industrial process like a nuclear plant or a chemical plant or a steel plant, we need to understand the engineering layers of protection there as well. We need to understand how the process actually works. A lot of this research actually came from what I was actually doing some research for ISO hydrocrackers, if anybody knows what those are. So like we see that the price of oil is $100, let's say $100 a barrel for light sweet crude. Nobody buys $100 barrel light sweet crude. What they do is they buy the junk at $30 to $50 a barrel instead, and then they run it through a process called a hydrocracker that actually runs it darn close to fusion, but they get high pressure, high temperature, and they basically get a product coming out of that about 98% perfect yield. So that's in other words one of the ways they make a lot more money off of in the oil and gas industry is by running through these hydrocrackers. They're very, very dangerous processes. However, when you look at it, let's say your given hydrocracker has 3 controllers in it typically. Right? They'll have a lot of physical protective measures, but usually there's only 3 electronic components on one. Right? Now, if you look at it and say, all right, fine, if you at this speed and at this temperature, if you shut down number 1, and then at this speed and this temperature at a different condition, you shut down number 3, and then at this condition, you shut down number 2, you're going to cause this thing to blow up. Well, if you have to do the math in your head a little bit, that's a pretty complex sequence of events. So in other words, statistically speaking, it's very unlikely that you're actually going to cause that big boom scenario to happen through just typical system failures. So what you see is there are maybe physical protective systems, but very rarely do we see electronic protective systems like protection over remote access control, protection of firewall, protection of antivirus, that kind of stuff. We very rarely see those components in there. But I was actually doing some research, and I do it with a couple of chemical engineers, and we very quickly showed, well, from a deterministic perspective, as an attacker, I could actually go in there and issue those commands to stop the controllers at exactly the right time and cause that really bad scenario to happen. Obviously, that got the attention of namely the government and a lot of the oil and gas folks. That earned me a seat on a project called the Logic Commission, LGIIC Phase 2. We spent about a year doing heavy testing on a number of industrial control systems, safety systems, and things like that, understanding exactly how would somebody be able to take control of a large, complex system electronically and to be able to use the system against itself. This is not a matter of launching a single vulnerability and the whole thing blowing up. This is a matter of chain exploits. This is a matter of understanding the physics, understanding the engineering to pull all this off. The other thing I remind people is that there's a difference between valid communications and possible communications. You know, the folks from the gentleman from Cisco that just spoke, and obviously I spend a lot of time on networking. We see a lot of people that make this mistake. They say, oh, there's only one connection between the process control environment and my IT environment, and that's my historian or a OSI Pi or some other device out there. Well, they understand that this is the only way they want communication to flow. However, if the network is wide open or it's flat, it can flow in any way that we want to make it flow. If somebody wants to take control of the system, they can, if they gain access to one component and the network's completely flat, they can talk to all of them. So in other words, again, single point vulnerabilities are also of minimal value to if somebody is trying to attack an industrial control system. Like I said, if you learn how to shut down a PLC remotely, that's really of very little value to you unless you understand all the components in the system. And again, the threat, one thing I also say is that the threat is just as effective and not worse than the attack. I've actually done forensic investigations in a number of cases where people have stolen data off of environmental control systems, they've stolen data out of laboratory systems and things like that, they've either manipulated the data or they've published the data to try to, they haven't actually manipulated the process at all, but they've just taken the data from the process and they've sent it out and tried to bring up environmental lawsuits and things like that against customers. We've seen a lot of that happen quite a few times. So in other words, I always try to remind people that it's not necessarily a matter of somebody actually hacking the system. You need to protect your information as well, because sometimes the threat of the attack is just as bad as the attack itself. Okay. From an industrial control perspective, the 2014 data breach incident report shows there was a threefold increase over 2013. Only just 256 incidents were on to OT, or what we call operational technology networks, were reported into the ICS.CERT. This is an industrial control system security CERT system. It's at us.cert.gov/control under our systems for those that are interested in it. And these are ones that were just voluntarily reported. That's just a little, that's a little bit less than one a day at this point. I'm aware of probably 256 happening within a couple of months in many cases. We actually, there's a lot higher. Everybody's got these scary charts, so the line's going way up very fast. But the bottom line is, yes, we're seeing a dramatic increase in interest and attacks in these environments. So let's understand a little bit about this. One thing that one fallacy I like to address head on is that people think that the idea of attacking like a hydrocracker or a power plant is the hacker's going to break in at 8:01 and at 8:03 the plant's going to blow up. That's really not the way it goes. Right? What we've seen is in research is the average time to compromise to the time of the attack is about 18 to 24 months. So we've been tracking folks out there that have been trying to do research, they've been researching targets, they've actually been gained access, from the time that they gain access to the network the first time, establishing what we call that bastion host, that first point of compromise, to the time that they actually launch an attack is usually anywhere from 18 to 24 months. All right, so in other words, during that time, they're researching, they're mapping, they're determining, they're trying to gather data off the network, they're tuning their malware, they're tuning their scripts, they're tuning their attack, and they're coming up with the overall strategy. And then by the time they actually launch the attack, they're probably going to know the network better than you do. Anybody here has heard of Stuxnet? Stuxnet's made all the news out there. Stuxnet had about 4 different versions that existed for up to 2 years before it was ever first detected. Right? Flame, Dooku, Havoc, some of those, again, existed for quite a while before they were ever even detected. So one thing I like to remind folks of these days is that if you're not watching the exfil of information off your network, you don't know what's going on. Most people look at the idea of blocking traffic from the firewalls coming into their network. I spend a lot more time in looking at data leaving the network, trying to see what information people are trying to actually, what are they trying to get off your network. And we've seen this happen in malware now. Flame and Dooku are information harvesting worms that are actually just, they're not doing anything as far as we can tell, beyond actually just sending data back out to a command and control center. Okay. True exploits are not even needed to attack an industrial process most of the time. I can go fire up Shodan, write a few Python scripts, and I can probably find, in fact, actually I'm 100% for finding information systems, industrial systems connected to the internet for almost every customer I've dealt with. Alright, so in other words, most of the time all I got to do is just find a couple of those systems. That's my first point of compromise, and very rarely do I even need some exploit. A lot of times all I have to do is use the valid command sets in the industrial protocols themselves. As Dr. Blunt pointed out this morning, they are very weak in many cases. They're built for robust and resilient communications. They're not built for security. They're built for performance. They're not, they're not designed. In fact, they're designed to run as fast as possible. We're talking about an industrial process. Sub-millisecond communications are almost always, are often needed, especially at things like substation automation. If it takes 300 milliseconds to get your emails, does anybody notice? Probably not. 300 milliseconds in my field can be all the difference between a process failing safe, or failing dangerously. That can be all the time in the world required for that. So, okay, a combination of factors required to move from the nuisance trips to more significant failures. So, when you have cybersecurity knowledge, in other words, you understand IT security, you understand cybersecurity, then you understand how the industrial process itself works, like you understand how a desalination works, you understand how you understand how water wastewater works, you understand how an ISO hydrocracker works, you understand the physics of the process. And then you know how the actual industrial control systems work themselves. And at that point, you will have all that you need to actually attack an industrial control system and cause quite a bit of damage. Now, interesting, this is some theory work that we came up with a couple of years ago. I said, well, hey, if anybody wants to get serious about writing malware for industrial control systems, they've got to write malware that comes up with all three of these things. Stuxnet came out a very short time later. The next year, I actually wrote a paper that theorized we were going to see a decoupling of the information gathering and the attack processes. So in other words, there was going to be worms that did nothing but gather information, and then there was going to be worms that actually did the attack. Then we saw Flame and Dooku. Last year, I did a bunch of work for one of the large energy holding companies. I did an assessment for all their plants and wrote a bunch of scenarios. I said, well, the next thing you're going to see is malware that's going to be attacking vendor websites and hijacking the downloads, that you're going to get malware from your firmware updates directly from the vendor and not even realize it. Then we saw Havocs just come out. This year I decided to keep my mouth shut. All right. Just a small sampling. We talked about those industrial protocols. This is just a quick snapshot of all the of a few of the protocols out there. And again, these are all built for robust, resilient, and speedy communications. They are not necessarily built for security. Not any stretch are they built for. My favorites, because I used to work for Rockwell, tend to be SIP, the Ethernet IP, Modbus, some of those. One thing I also like to make, if you're actually doing analysis on an industrial network, you need to understand a little bit about the shape of communications for industry. And I realize this is an oversimplification. But if you look at your typical IT environment, let's say I'm going to go out and I'm going to get a web page. How does that communication get constructed? What happens there? All right? It's going to be probably a fairly short TCP time. In other words, I'm going to open up the session. I'm going to go out to, pick your favorite website. I'm going to get the information. I'm going to download the information on that page. The session is going to be constructed and deconstructed within a few seconds. Then I'm going to look at the information. Then I'm going to click on a link. I'm going to go out and do the whole thing again. That's like a typical web browser communication. Very short TCP times. But also going to follow the shortest path off the network most of the time. Right? I'm going to follow the closest to the next router up, the next switch up, the edge device, and out the internet and back. I'm telling you, that's when we do that from a performance standpoint. Rarely time critical below a few seconds. Again, if it takes me 300 milliseconds to check my email, I'm probably not going to notice a thing. For an industrial control system, however, we did a modeling example of this. A single process control instruction, a single instruction can take as many as 19 different TCP connections in order to complete the instruction. Most of those communications are going to actually happen at these lower layers, device to device, device to server, and then back down. So you're going to know, we've heard some of the terms this morning like HMI. HMI is a human machine interface. It's a PC, right? It's a screen that people interact with. So they're going to issue the command. That's going to go out and validate whether the command is actually allowed to happen. It's going to update a historian. Then it's going to go out to the controller. It's going to tell it to increase by 5% per se. Then there's going to be a verification. In other words, it's going to happen out here. These are going to be highly matrix communications. It's also characterized by very long TCP socket times. I'm going to open them up, and I may leave them up for hours in some cases. So the reason I bring this up is if you're using your traditional IT techniques for analyzing a network, you're probably not looking at the correct thing. Because in this chain, if there is even a single blip at any given point in there, let's say again, that 300 millisecond pulse we've been talking about, you get a little bit more than 300 milliseconds, and the entire chain of 19 different TCP sessions could fall down, right? So in other words, when we design an industrial control system, what I normally do is over-design the heck out of it from an IT perspective. In other words, there is a huge amount of capacity, availability, and redundancy. You're like, why the heck would you need all those redundant switches and things for a device for 2% utilization on the network? Well, the reason for that is we designed for the speed of communications. We care more about latency of communications than we do about the bandwidth a lot of times, or about the quality of service. Anyway, okay. So from an attack mode perspective, anybody here familiar with the STRIDE methodology? In Microsoft, look at spoofing, tamping, repudiation, denial of service. These are a lot of the attack modes we look at for industrial control systems, for IT systems. Normally, I will just start with like a STRIDE model when I'm trying to understand how an industrial control system will be attacked. And then we look at the model-specific, model ICS. I'm a Linux head, by the way, and this is a new toy, so don't. Okay, so looking at the ICS-specific attacks, these are the attack modes that we're normally looking at when we try to analyze an industrial control system. Loss of view. I'll explain this a little bit. The idea here is the first thing I want to do is decouple the actual state of the process with what the operator is seeing. So, like for example, anybody familiar with the 2005 when the Texas City refinery explosion happened? Yeah, okay. That's an example we use quite a bit. It's not a hack attack, but we use this quite a bit in our space to understand how these things occur. One of the key things that happened there was a fluid stack that should have been no higher than 6 feet high. There should have been no more than 6 feet worth of material in that fluid stack at any given point. Well, there was a sensor failure. So in other words, what was happening in the actual process is not what the operators were seeing. And so the operators kept filling this fluid stack higher and higher and higher, thinking that it was still below 6 feet. They kept adding material in over and over and over again. And they did this over a period of hours. Again, one of the things that we see very typical in an actual failure in an industrial plant is they typically build up over anywhere from about 12 to 18 hours too. They're not something that just happens right away. So anyway, they kept adding material to the stack. Eventually, it overflowed the top of the stack, and they created what we call a vapor cloud. It's not a very good thing. I saw the picture of the Moab bomb out here a few months ago. Very similar concept. We put a whole lot of fuel in the air, disperse it over an area, and then we find a way to ignite it. Well, that's exactly what happened at Texas City, and somebody fired up a truck, and when they fired that truck up, it sparked the vapor cloud, and then blew the place to hot heck. Right? Okay. So the first thing I want to do as an attacker is create a loss of use scenario. I'm going to decouple usage. You don't know it. I can do that through locking you out of the HMI. I can do it through, and the second one is the manipulation view. I can tell you that it's 4 feet, when it's really 6 feet, or it's really 20 feet, or something like that. So in other words, like man-in-the-middle attacks, things like that, are the things I'm typically going to be looking for here. It's going to decouple the view so that the operator, if they're staring at their screen, what they actually see in front of them is not what's actually going on. So again, manipulation of view is the loss of view happens all the time. And we have slow network updates, we have processor errors, we have all kinds of things out there. So in other words, loss of view is not necessarily an intentional attack. But when a plant describes to me that they're having problems with slow HMI updates or they're losing data, I start looking and saying, okay, I know we need to attack here because these weaknesses that you're currently experiencing are the same ones that an attacker is going to look for. So we start looking at how we're going to do our network defenses to be able to design a network that's not going to have these type of latency issues in there. Then we get into a denial of control scenario. Denial of control is kind of like denial of service, but the idea with denial of control is I'm going to make it impossible for the operators to be able to interact with the process the way they normally do. In other words, they're not going to be able to push those buttons on the HMI. They're not going to be able to issue commands from their computers. They're not going to be able to use their smartphones to talk to the drive because I'm going to block them out of all those communications. I'm going to deny their ability to control the process through their normal means. However, in this situation, a lot of times, there's emergency stops, there's other valves, piping, there's physical things they could do, so that if they catch it in time, they could still go out there and, with a monkey wrench, they could go out and change the process and probably keep things from getting worse. But then we get into manipulation of control. This is where I now am filling material into a chemical tank or something like that faster than they can actually compensate for it. So there's I think from about 2004, Idaho National Labs put out a demonstration that's pretty good on overflowing a chemical tank. They did it remotely over the internet. That's what we call manipulation of control. Somebody remotely took over the drives and kept pumping material into the chemical tank, and they simulated a chemical overflow. And then the last one is a loss of control. Loss of control is when the physics of the process take over. Forget about it. If you have no opportunity, you better be running because something's going to go very horribly wrong very shortly. So in other words, when I'm looking at it, we're doing threat tree analysis, we're doing vulnerability analysis, and we're doing a vulnerability assessment for an industrial setting. These are the additional things that we need to look for. What are the opportunities that an attacker has to deny you the ability to see what's happening in the process or deny your ability to control the process? So in order to do this, not only do I need to understand the IT security, I need to understand the engineering controls and how they work too. All right. Really quickly on this slide, I won't spend too much time on this. One thing I will say is that, when we start looking at what we call directed hazard analysis and mitigation, this is the idea of, so when I go through and I look at processes, I say, here's 4 different ways that this process could blow up. Right? Here's the worst case scenario in 4 different ways. I want to look at now, those are things they say could happen in nature. Okay, we're worried about this, if you hit this temperature, we can cause an explosion or vapor cloud expansion. Now I'm going to look at, well, how would somebody actually do this if they were an intentional attacker? What information do they need? What level of knowledge they need? What steps and sequences would they go through in order to be able to cause the exact same scenario? Right? So some examples that they might be looking at use misdirection with forging alarms. Like the big power outage that happened up in the Northeast, everybody's probably familiar with a few years ago. One of the exacerbating things that happened there was that there was so much alarm and event traffic that it caused an unintentional denial of service. So part of the thing that happened there is that stations did exactly what they were supposed to do. They could not communicate, so they shut down. Right? Because they had so much alarm and event traffic. So, hey, alarm's got to be a good thing. Let the guys know what's going on. In 1994, we had the Texaco refinery explosion. They had as many as 30 critical alarms being generated a minute before that place actually blew up. 30 critical alarms a minute. How many people here could be able to respond to that? Right? So in other words, it is entirely possible to oversaturate your operators. In fact, we have a whole standards body out there, ISA 18, that is designed to what we call alarm rationalization. The idea of how much information do we present to an operator in what amount of time? How do we not oversaturate the operators? Okay. Drop all network traffic simultaneously, deny or manipulate control variables in the correct sequence to create a hazard condition. These are all some of the various things I might be looking for. So from an industrial perspective, the first place I start is not necessarily the network diagram. The network diagram is where most people usually will start. How's the network actually architected? I'll usually start with the process diagram. We're going to look at what we call the piping and instrument diagram. That's the PNID, the process hazard analysis, the PHA, and the HAZOPS hazard analysis. Those are studies that will be done at any engineering facility to tell you what the worst case scenarios are. They're done from an engineering perspective. I know I'm throwing a lot of acronyms around. You're not an engineer, folks, and you're probably not going to know what all of these are, but we'll try to explain as well as I can. Basically, what I'm trying to say here, though, is if you go into an industrial setting, you go down here to Brownsburg nuclear plant, you go down to the steel mills in Birmingham, those folks, you'll be able to go, and they will have already done the worst case scenario failure modeling for you. They're going to know what those are from an industrial, from a safety perspective already. As a cyber attack, as a cybersecurity expert, your next role is actually to figure out how would somebody be able to do that intentionally, not just that something happening from an accident perspective. So then I'm going to review those safety hazards and major safety hazards and financial losses. I'm going to test the industrial control devices. BPCS is the basic process control system, and SIS are electronic systems. They're highly robust systems called safety instrument systems. They're another electronic component that we use that are more robust than your typical PLC, but they cost a lot more, so people don't necessarily buy those a lot of times when maybe they should. Measure the control performance, measure the network performance for the conditions, analyze for directed and unintentional threats. Some of the types of things we look for, we want to look for what would happen at high temperature scenarios, what would happen at low temperature scenarios. From the power plant, go again, what's actually more dangerous? Is a surge more dangerous or is a brownout more dangerous for most electronic components? All right? Most folks think it's the surge. No, usually it's the brownout. That's what actually causes, in other words, a sag in the electronics, the electrical voltage is actually more damaging to electrical components a lot of times than the surge is. A lot of times we build surge protection, we don't build sag protection, right? Anyway, just a lot. High temperature, low temperature, high pressure, low pressure, flammable process, toxic reactions. Anybody that's, your trains that knock over and they release chlorine gas, everybody gets really excited for a few minutes. Those are the type of things we look for. In other words, where are those hazardous conditions in the plant that we understand that we need to protect the process from? So there again, we also are looking at this. The next thing I need to look at is how do I bypass the controller set points, I/O values, the commands of controllers, alarm conditions, safety interlocks, interconnector integrated. I didn't see really many engineers in the room, so I won't spend a lot of time talking about this. I'll say that these are all things that are integral to an industrial process and how they work. So a set point, for example, would be run the machine at 500 RPM. Right? That would be a set point. So I would issue commands. If I wanted to be able to vary that speed up and down, I might issue commands to go to 1,000 RPM, 10 RPM, and then 50 RPM, and then 500. Manipulate that speed up and down. By the way, this is what Stuxnet did to the centrifuge. The idea with Stuxnet is that it would vary the speed of the centrifuge up and down while it falsely, guess what, manipulation of view, right? While it falsely reported the speed as being accurate, it was actually ramping the speed up, ramping it down, ramping it up, and doing this, trying to create a premature physical failure inside the centrifuge. My theory is that actually Stuxnet was a failure. I think they got a little bit overzealous. I think that what they meant to do was cause enough disruption to the enrichment process that it would have taken many years to figure out, lots of scientists and experts and everything else to figure out what happened. Instead, they got a little bit overzealous and actually caused some failures a little bit earlier than they meant to, which got people looking, and then they started figuring out what Stuxnet was. Again, it existed for over 2 years in multiple forms before it was ever even detected the first time. So again, I think even though Stuxnet was kind of we look at it as a deterrent to the Iranian nuclear enrichment or whatever, I actually think it was probably a failure. It was probably an unintentional failure. But anyway, so these are all things, input-output values, commanded input-output values are going to be actual voltage. So if I'm expecting a 24-volt pulse every 500 milliseconds in order to maintain communications, I may go in there and I might send a 5-volt. I may just send it at the wrong time. Some of those cause actual field. Again, we're using information to control physics. Right? We'll spend too much time on that. Impact categorization for industrial control system. This is what I said, again. Now I know, like in an IT space, losing your business systems, losing web pages, losing information, confidential information, those result in lawsuits, that result in having to buy credit monitoring from folks, that result in they can be rather disastrous impacts, don't get me wrong. Right? But a lot of times those worst case failure scenarios for an IT environment are just kind of where we start from an impact scenario for industrial controls. So the first thing we have is what are called nuisance trips. Nuisance trips are just basically the incorrect values are received by the process, and the process shuts down. It does exactly what it's designed to do. Maintenance guys go out there, they turn a couple of volts, people go out, they reissue commands, and everything comes back up, and it goes again. Usually, and again, these numbers will vary wildly depending on what environment you're in, but a typical cost of a nuisance trip is going to be about $500,000. Now, that may not sound like a whole lot for a plant that's making $30 million a day, but let's say I generate one of those nuisance trips every 30 minutes. Right? Okay? Level 1, got a nuisance trip. Number 2, unplanned outages. This is where, again, we weren't planned or we weren't scheduled to be down, but I caused enough issues out there, sustained issues, you're going to be down for a few hours. Typical downtime, again, these numbers can vary wildly, but for a typical manufacturing facility, downtime can be anywhere from $2 to $8 million an hour. I was involved in one with Caterpillar a few years ago, where again they estimated a 3-hour loss at over $8 million. Now again, measuring downtimes is also a very weird science, but we're talking about a fairly large economy of scale. I dealt with pharmaceuticals a few years ago. A single batch was $30 million. Corrupt any point in that $30 million batch, you lose the entire batch. That's a pretty big deal, right? So, okay. Then we get into sustained outages. Unplanned outage would probably be anywhere from a few minutes to a few hours, right? Then we get into sustained outage. This would be like, let's say I went in and I rewrote the firmware, all the controllers, so now somebody's got just a bunch of bricks out there, and they've got to go reinstall a bunch of equipment. You're talking about days here at this point. So sustained outage, there again, you're talking about millions of dollars per hour, protracted out over many days. Now, sometimes they recover from this, and sometimes they can't. Then the worst one, we get into what we call dangerous failures. This is where now we get into bumps, trips, falls, we get into machine equipment knocking people over, we get into fires, explosions, and then we start getting into crater factor stuff. So you're talking about anywhere from somebody getting their elbow bumped. For example, I was doing one on a 1,200 bottle per minute filler a couple of years ago. Basically, it's a giant spinning centrifuge that's loaded with glass. It happened to be pouring beer into it. So anyway, it was really bad. But when it failed, it threw glass up to a couple hundred yards away. Right?
You're talking about a fairly, I mean, you're talking, take something, okay, there's a wonderful beer going around, centrifuge, and the next thing you know, it blows up, and it's sitting glass almost 200 yards away inside the facility. That's obviously a very dangerous scenario. Or again, oil and gas facility. When BP Texas City, I think it was 14 people were killed instantly, if I remember right. That was pretty high, anyway. That was pretty high for that particular scenario. But you're talking about the fact that once something like this, you get into a loss of control scenario, things happen really quickly. Some example scenarios. I don't spend too much time with these if you're not engineering folks. I'm not actually one anyway. But also, like, again, you might look at your typical industrial process. You have a safety valve, speed transmitter, disconnect switch. When we go through and we do our analysis during a vulnerability assessment, we will start here most of the time to understand what are the failure mechanisms within the process itself we need to be worried about. So we'll develop a scenario that says, how are we going to compromise this from an engineering perspective first? So disable lower speed trip system, disconnect the load from the generator, and then open local disconnect switches or power distributors or consumers. And then, for example, we know that's how we're going to cause a surge condition on the generator. This is oversimplified greatly. The actual process we did for this was about 30 steps. Right. So anyway, kind of condensed down into this. Here are the steps that we would go through to freeze the value speed transmitter, disconnect it, and then put the generator in a surge condition. Again, surge causes a high amount of vibration. So you're talking about these turbo generators are usually pretty large pieces of equipment. So again, if one goes into this, it's going to vibrate, it's going to fly off the rails. If anybody's ever seen, there's the Aurora vulnerability that was done by International Labs. They put together a video of them destroying a diesel power generator by basically putting it into a surge condition. And you can see the video, the thing starts to shake and it starts blowing parts off, and the magic smoke escapes. Right? Okay. Once we do the engineering steps, then we're going to go through and we're going to go through what would the IT steps be required. Now, this is just one very simple scenario. Like, for example, everybody's seen the lines before, how would I conduct the surveillance? So, in other words, what would these steps behind this? What information do I need? I'm a big fan of open source intelligence techniques, and I do a lot of this work, going out to Shodan, going out to Google, running my own scripts, going out to the integrators, the people that deploy these systems, because their security protection is probably not nearly as good as the owners that own the systems. Right? They're the ones that deploy them. They don't, this might be a mom and pop shop, for example. They probably don't have the same protections, but I could probably find all of those diagrams I needed at a lot of those integrators. Conduct the surveillance, how I'm going to map the systems to figure out what components are there, how am I going to find the vendors that are there. That can be as simple as going out to, let's say your local power utilities or water utilities. They put projects out for open bid all the time. Very often, you can get those RFPs, and they will have a lot of information, including locations, type, vendor, model, everything else will be in those RFPs, and they are publicly available when they come out. We've been working with vendors for quite a while to try to clamp some of that down and make it not quite so open. But again, just where the laws out there for the requirements for open bid, open specifications, actually are kind of a hampered process in some for many of these folks. First steps of initial affecting and compromise. Again, what am I bastion host? How am I going to establish the first workstation with the environment? What I always tell folks here is that eventually, at some point, the IT steps, the IT security steps are going to stop, and the engineering steps are going to take over. In other words, those steps we just went through a few minutes ago, I'm building up to that scenario through all this. So how do I find out all those components where they are? At that point, I'm going to make my initial compromises. I'm going to deploy some type of rootkit bots. I don't care, worms, whatever you come up with. Probably, the APT word is so badly overused, it's not even funny. I think we got to add APT to the drink list we mentioned a moment ago. But anyway, APT is badly overused, but a lot of companies these days are using that to talk exactly about what I'm discussing today. The idea that now we're going to have, we're going to have custom, fit-for-purpose malware that's going to be written for these environments, that's going to go out and map the environments, use the industrial protocols like Modbus, Ethernet IP, or SIP, that's going to map the components, map the systems. They're going to then exfil the information off the network to a command and control center. This is exactly how Stuxnet works. Stuxnet, the main vector of compromise ended up being the USB exploit. Good gosh, I thought about it a while. There was anyway, it's not important at the moment. Anyway, one of the main compromises was actually through USB keys. That was in like the fourth version of Stuxnet. It actually was in an early version of Stuxnet. They took it out because they thought it was useless, and then they later found out, no, that actually was the best way to do it, and they put it back in. So you're talking about the information that they got off the network by the command and control centers reporting the data back to them is what they used to tune it so that it was more effectively able to map and find its targets. I can talk about Stuxnet for quite a while. That one actually got pretty LNK exploits. Thank you. Sorry. LNK was getting the link file exploits. But yeah, so anyway, in other words, this is actually tuned over a period of time, and again, we used this for years to figure out how to actually attack a process. So by the time it actually inserted the required process knowledge and engineering steps, again, we knew more about the process than they did. Okay. Then we're going to prepare the final attack. Again, this takes where you write the attack script. What are the steps? Like, for example, disconnecting the load, adding fuel, any of those kind of things. And at some point, then we're going to initiate the attack by launching it through the command and control center. This is just one potential sequence of events. Depending upon when I go through my model and environment, we may determine, for example, the only way you're going to pull this off is if you have an enlightened insider, somebody that actually has physical access to the plant. That would just change the attack process. That would say, hey, then at that point, now we're talking about nation-state level attack, we're talking about level, we're going to do extortion, we're going to do all kinds of other things in order to be able to get somebody to help us actually conduct an attack. Or maybe we'll hire the guy that filmed himself on YouTube breaking it. I don't know. So, anyway. Okay. So a really quick example study, and I'll let you guys go for lunch, is I actually did this for a steel mill in our backyard. Excuse me. Okay. In other words, this was not far away. But so here we had a large melting process, we call it a cumulative melt process for a steel mill. And it had an energized close. In other words, as long as the component was energized, it held a door closed that had a water tower on top of it, with water, and there was the emergency coolant. So in other words, if there was a critical failure in the melter, all right, what would happen is they would just de-energize that component, and the water would flow into the melter, would cool it, give it an emergency cooling, it would shut the whole thing down and render it to a safe state. When we were actually doing the testing of that component, I found out that about 4 out of 5 times, I could cause that component to fail energized. In other words, it would report that it was open. It would report that everything was fine, but it was actually failed in energized condition. In other words, I left the door closed while we were actually doing it. I didn't do it on the actual melter. We did it on sample equipment, obviously. But we would have left the door closed, and we would have generated traffic in this particular way. So then, obviously, we came up with an attack script that said, I'm going to generate this type of traffic, I'm going to energize close this particular, the emergency backup, and then I'm going to issue commands to stop the blowers and stop pressurized water, which is how they regulate temperature most of the time, and then I'm going to open the valve to throw as much oxygen into the process as I can. Time of reaction was less than 3 minutes. Right? In other words, from the time that we would have done all that to the time the engineers told us that they would have actually probably killed about 50 people through that, was less than 3 minutes. Right? So in other words, it would take me a long time to get that information since you successfully compromised at that point. But by the time I actually launched the attack, you're talking about loss of control happening within a very short amount of time. In other words, not enough time to react and get everybody to safety. All right? Okay. So, really quickly, again, between lunch, I think hopefully we got you there, you're really right there. I was actually was a co-author of a book in this space. There's more information about that. There are also a number of other really good authors out there. I'd be glad to give you guys a list of recommendations, some folks to talk to. There's my contact information, and I will leave it at that. So, are there any questions I can answer for anybody real quick before we break for lunch?
Well, you didn't cover that the gas generator up in Connecticut. Do you remember that one that blew up?
Mm-hmm.
And that it was very similar to that one that you explained in Texas, how it backfed the room with the gas and then the oxygen and somebody.
Yeah, absolutely. And that's we actually in my company, I run the cybersecurity services, but the other half of my company, actually most of it, is actually an industrial safety company. And so we have a large database of all kinds of failures like this happening on pipelines, like pipelines, oil and gas refineries, and around the world. So yeah,
gas generators like the latest.
Oh yeah, those are in their. I hate to say it this way, and that's part of the problem. That people say, oh, they'd be really hard to take down because you have all the machine protective systems in place. Like, okay, there's 2 things. Number 1, there are ways to bypass or to shut down the protective systems if you're not careful. Right? Number 2, if I do it fast enough, in other words, if I ramp the speed fast enough or something like that, then I can usually bypass those systems. I can actually overrun their ability to protect. So, yeah, those are the things that I'm usually looking for when we're doing the analysis of what types of scenario. Even though there may be all these physical piping, there may be physical relief valves and that kind of stuff, and emergency relief valves, even though those components may exist, the fine, you can't do this because you can't overflow this chemical tank because there's a hardwired level switch. If I do it fast enough, a lot of times I can't, because by the time the component sets up, there's still enough material in the pipes that's going to be piped in and makes it overflow. So a lot of times, again, we have to do that level of analysis to understand what those threat factors are.
Yeah, I think they didn't exhaust the gas properly.
Right.
Or they reversed it somehow.
Yeah, you can. Yeah, exactly. A lot of times I've seen people can actually, even though the valves, the fan may be designed to go one way, you can't turn it the other way. You can just reverse the polarity, for example. Right. Okay. Any other questions? All right. Okay, good. Thank you all very much. I appreciate it.